In this video, we are going to simulate cymatics using max and jitter. Cymatics is essentially the study of sound reflected upon the physical plane. A good example of this are Chladni patterns. These are patterns that arise when you pour a bunch of sand over some kind of plate and then make that plate vibrate at specific frequencies. Since it's not so easy to pour a bunch of sand into a max patch, we are instead going to be looking at particle systems using jit.gen mesh and implementing specific mathematical algorithms on jit.gen. Let's see how this is all possible. And here we are. It's the semi-empty patch that we are going to start with. There is this little formula here I put, so we are going to use this for our cymatics simulation. But before that, I want to kind of explain how this works, right? And there's a really nice website about this, or a web page about this, creating Chladni Patterns, which is, let's call it a subspecies of cymatics. And in this page, this person describes a mathematical formula or the logic that makes it possible to input some parameters and get these kinds of nice visual effects. You will see though that this is a bit complicated, right? At least it is for me. I'm not a mathematical wizard, so when I read things like this, I get a bit confused when it says things like, we know that h is a standing wave. This tells us that h must be in the form h x y t equals sine of 2 pi times f times t times s x y. This means that time uniformly affects the magnitude of the height of the plate, but we know there are nodal points at the center of the plate and at the edges that gives us those extra
this says
equations.
that s is a weighted
0,
sum
0
of
equals
sine
0,
products
since s is a standing wave,
plus
1 y
equals
equals
f0
f0 boundary of the
clever
that
is
essentially
x
equals
equals
pi times y equals
only
pi
there
times
we
keep things pi times n.
This is a very well-known differential
and
equation.
this squared plus m squared eigenfunction.
Since the height of the plate is a wave
propagating over the plate surface, we can substitute our current formula. The point is, it's really complicated, and I don't want to work with that kind of complicated right now, so I boiled it down to this formula that we are going to implement using a particle system, right? Because that's what cymatics is. That's how Chladni patterns are demonstrated, by putting a bunch of sand on a plate and then making that plate vibrate by certain frequencies, and these multiple frequencies clashing against each other create these patterns. So let's start by simulating sand. I'm going to create a jit.world. Let's call it cymatics. I'm going to enable floating window style and FSAA, full scene anti-aliasing. Okay, and then I can toggle this jit.world on, and now I need a bunch of particles, so a matrix, a jitter matrix containing the data for all these particles, and also a way to display them. And I can display them by using jit.gen mesh. Let's give it the argument of our jitter world context, and I just need to tell jit.gen mesh that it's going to draw points, so draw mode points. And let's also give it a color of 1111, meaning a white color. Okay, so just to visualize something, I can use jit.noise, right? This is a very classic way of just putting a bunch of points on the screen. I can give it 3 planes, the float 32 data type, and since I love sands, I'm going to create 100,000 particles. So this jitter noise is going to create a matrix with 100,000 cells, each with a random value that goes from 0 to 1 on 3 planes. Of course, to trigger this, I need to create a button, connect it, and voila. Alright, so since these values go from 0 to 1, of course, they're only on the top right of the screen because 0, 0 is the middle in the world of jit.gen. And we can fix this by simply using jit.map. We have to use the map attribute and then tell it the input range and the output range. So the input range is 0 to 1, and I want it to be between -1 to 1. And doing this, we'll just put everything in the middle and spread it nice and evenly. But before I take this and I load this up to another jitter matrix that I'm going to use to create these cymatics with, I need to make sure that the z-axis is not random. So what do I mean by this? If I use jit.gl handle and connect it to my jit.gl mesh, I can kind of rotate this, and as you will see, this is three-dimensional, right? Of course, because all of these three planes are going to have random values, but I want to simulate a bunch of sand on a plate, not spread out evenly on a cube. So I want to eliminate the z-axis. I want to make sure it is 0 while I keep the other two planes. So the first two planes are these values. The third plane is going to be 0. And let's use jit.gen for this to kind of warm us up for the heavier jit.gen that is going to come up. So I'm going to take the results of whatever's going on in here. And as you know, I can command double click or lock and double click my jit.gen to open the gen patcher, which is pretty similar to the max environment, but slightly different. And I know that whatever comes in here and whatever goes out is going to be applied to every cell. So I'm defining a process in this jit.gen that will happen to every cell of the incoming matrix. So what do I want to do? Well, I want to take apart the x and y values or planes of my incoming cell. So I'm going to use Swiss X and Swiss Y, and then I'm going to pack those values into a vector, which is fancy jit.gen speak for list. Meaning that if I say vec 0, 0, 0, this is going to be a list of 3 elements matching the 3 planes of my incoming matrix. And I'm going to make the X value of my incoming cell the first element, the Y value, the second element, and the third one I'm going to leave empty. So it's going to use the third argument, which is 0, which means a Z value or the third plane or the third axis, whatever you want to call it, will always be 0. Okay, and now if I generate random noise again, there it is. Now it looks like a plane. The X and Y coordinates are randomized, but the Z value is always 0. Perfect. Okay, now I'm ready to load this up into another matrix. Now I'm going to create another jitter matrix and I'm going to give it a name. Let's call it sand, because I'm going to use kind of a feedback loop. I'm going to do something to this jit matrix sand, and then I'm going to take the results and I'm going to put it back into the same jitter matrix. Let's also give it the same arguments. So 3 planes, float 32, 100,000. So that's a lot. Elements. Right, and how are we going to do the feedback loop? Well, I'm going to need another jit.gen here. Right, so I'm going to leave this empty for now, but something is going to happen in this jit.gen, and then the result, which is the result of this formula, we are going to get into that in just a minute, but the result is going to be loaded into the same jitter matrix. So if I create another jit.matrix and I give it the same name, it is going to refer to the same matrix. So a setup like this is very classic for using feedback systems, especially when we are using particle systems. So now I just have to bang this once to load this matrix into my sand jitter matrix. And now if I send a bang to this jitter matrix, it's going to go through jit.gen, it's going to take the results and it's going to update itself. And then when I send it another bang, it is going to repeat this process. And of course, I do have a lot of bangs in my patcher because the second outlet of jit.world is going to send out a bang per frame. So ideally about 60 times per second. So I can simply do this, and now this jit.matrix that I named sand is constantly refreshing itself. But nothing is happening. And why isn't anything happening? Well, there is nothing interesting in this jit.gen. I mean, I can try to do something boring. See, if I remove everything, it all disappeared. I can add 0.0001 to whatever is coming in. So the position of these sands would kind of start moving. You see what's happening? They're very, very slowly moving. Can make it a bit faster if I want. There we go. There it goes. Goodbye. And I can bring it back in and it will always float away because this is a feedback loop. But of course, that is not what I really want to do. I think this is better. Let's just make it stand in its place until we actually get into our formula. And for simplicity's sake, I'm just going to copy this and paste it in my jit.gen patcher for the feedback loop. Now, what am I trying to do here? I'm trying to figure out the Chladni pattern by looking at the vibrations of every sand particle. This formula here that, again, we are going to implement in this jit.gen patcher is looking at the position of each little speck of sand, each particle of sand here, and is trying to figure out how much that sand would vibrate, so how much it would go in a random direction, depending on the frequency of the vibrating plane. Because if it's at a position where it's not vibrating a lot, it would kind of stand still. It would be a part of the pattern that would be revealed. But if it's at a part where it vibrates a lot, so it's going to be thrown off to a completely random place, then that area would eventually be empty, and it would be part of the pattern that is empty, part of the pattern that is not a pattern. If that does not make a lot of sense, which it might not, it's okay. You will understand it better when we actually implement it. But the point is, I know my parameters and I know what I have to put my incoming values through. So let's start by creating our parameters. First, I need my n and m values, which are my two frequencies. It is the clashing of these two frequencies that are going to generate the patterns. So let's say param n, and then I can use some attributes like, let's make it a default of 1, let's make it minimum 0, maximum, I don't know, 100. And then I can copy this and I can just change the name of the parameters. So now we have our m and n parameters. And then I need a vibration parameter, right? This is how much are these particles going to vibrate. This is something you can also modulate. You can also change this to create interesting effects. Let's call it vibration and spell it nice. Let's give it a default of 0.05. We want this to be very low so we can really observe the particles moving, but we can have a maximum, minimum of 0 and maximum of, let's say, 10. That's a bit too much, but why not? Why not play around with it? Okay, now let's start implementing this algorithm. And before I do this, as a precaution, I'm going to remove this patch code because I don't want my matrix here to get updated as I'm implementing the particle, since, you know, that might create some weird results, or it might even crash the entire patch, which would make me very, very unhappy. Okay. So the position, actually that's not true, let's say the force we are going to apply to each incoming particle is this. The sine of pi times m times x. M here is the parameter m, or second frequency, and x is the x position of the incoming cell, the x position of the incoming particle, times sine of pi times n times y. We take this, we multiply these two together, and we add sine of pi times n times x times sine of pi times m times y. So, and after we add all of these together, we multiply it by the vibration. All right, so, well, first of all, we need to split the x and y coordinates of these particles, right? So again, I can use the Swiss x and Swiss y objects. And then I see a pattern here. Each time we are using this sine function, we are always multiplying m or n with pi, right? So I can already do this because when I declare a parameter, it immediately has an outlet. So I can use the times pi operator, and this will only work in gen, right? Because gen knows what pi is. It's already defined. It's a constant. And I can take these results. There we go. And then I can refer to these when I'm doing my own stuff. So let's start. So how do we get the sine of something? Well, I just use the sine operator, right? And I need to get the sine of pi times m times x. I have my pi times m right here, so I just have to use the multiplication operator. So x times pi times m, and then we're going to get the sine of that. Great, so that's the first part. Then we need to multiply this with, again, the sine of pi times n times y. Right, so again, the multiplication operator, y times n times pi. See, so it's not as complicated as it looks. Okay, so we have to multiply these two guys together. So this times that, and then we are going to add this up with something similar, right? So I can in fact just copy this whole thing, because I need to get the sine of pi times n times x. So x times pi times n. And then last but not least, pi times m times y. if you have a good feeling for this, you will see that this is essentially all the possible combinations of multiplying x and y with the pi of n and the pi times n and pi times m. If you don't have a good eye or a feeling about this, you're just applying this nice formula here and you don't need to worry about the details. But okay, so we have this part and now we just have to add these together by using the plus operator. Here it is. These are added up together, and last but not least, we have to multiply this by vibration, right? So I can create another multiplication operator and I can simply drag this here and do it like this. Perfect. Okay, so this is the force, right? So this is how much the incoming position of the sand particle is going to move. But the movement itself is to a random direction. So let's try to figure out a random direction. And in jit.gen, there is a nice way of doing this that is called the noise operator, which is going to generate a random noise, I believe, from 0 to 1. Right? Well, we can check this if we want. Let's make the output just noise. And now if I make my jit matrix sand go through this, yep, as you can see, the resulting noise, random values that is being sent to the resulting sand and then eventually to jit.gl mesh is on the top right, which means the values are between 0 and 1. Okay, back to our plate, back to jit.gen. So I know these values are going to be between 0 and 1, but I want the random value to be between 0 and whatever this vibration is, right? So I can take the results of my formula here, which is how much a particle is allowed to move based on its position, and I can multiply it by noise to say, look, this is how much you are going to move. And I can add the results to my original position, right? So I can take in one and I can add whatever the result of this is here. And then I can send this out. Right, so I'm getting a random value. I'm making sure it moves only by a certain amount in a random direction based on its position. And then I'm adding this to my current position, moving it essentially in that position. But of course, the problem is the random noise here is going to go from 0 to 1. So the random movement will be unidirectional. And I want it to be possible that it can also, go to the other direction, right? Maybe instead of going to right, I want it to go to left. So maybe before I do this, I can take my noise and I can scale it. Again, the scale object, very similar to the scale object in Max. Normally it goes from 0 to 1, but I want it to go from -1 to 1. And this should theoretically, ideally, make it all better. Wait, I made a little mistake. When I was creating these parameters, I used the attribute of default, which should work, but it does not always work for whatever reason. So now I have put the default value as an argument instead of an attribute. So param n2 and param m1, the 2 and 1 are the default values, which we can change later. I also got the absolute value of this part of the equation, so the part of the equation before I multiply it with v, because it just gives better results. No reason to think why exactly that is the case. Right, so I can again put this back in, and now everything is theoretically set, so I can slightly nudge these sands towards their destination. As you can see, each time the particles go through this process, they're beginning to take shape. And instead of me clicking this a billion times, maybe we can just use the banks coming out of JIT worlds. Okay, and this does look like Cymatics. This does also look 3D. Now, this is a cool 3D look, so you might want to keep this, especially if you're going to do something 3D with your patterns, but this is not sands on a plate for me. And I know that the problem is this noise right here. The noise operator or function here generates as much noise as there are planes, right? And since the incoming jitter matrix has 3 planes, this noise is going to have 3 planes, so we are always going to add a bit of Z, a bit of that third plane, a bit of movement on the third axis when we are nudging the sands. And if I don't want to do that, I'll simply do the same trick I have done before. I'm going to swizzle out the X and Y values of my movements. And I'm going to pack these into a vector that by default has 3 zeros. The first 2 planes of this vector are filled, but the third one is left 0. So there will not be any movement on the Z-axis. And now if I restart this, this should stay like a plane while still doing the cool Chladni patterns, which is nice. Okay, so now each time I restart this, as you can see, it is going to settle down into this specific pattern. The parts where it's empty are parts where there's a lot of vibration, so the sand particles are being thrown out to all kinds of places. And the parts where we can actually see the pattern are parts where there is not a lot of vibration. So if a particle lands there, it's kind of just stays there or does not move too far away. Of course, the part of the fun that is Chladni Patterns or Cymatics is messing with the parameters, and we have 2 frequencies here and vibration, so let's do that. Let's create a message box and $1 and then M, not that, a message box M, $1, and then we can connect this to our jit.gen. And if I create floating point number boxes, I can actually start changing these values. So I can make it, I know, 4 against 2. See, it immediately changes. Or I can by hand slowly change these values, and these are all going to create different patterns. 4 against 8.9, 2.7 against, I don't know, 5.7. And I can even try to change these dynamically in order to create cooler patterns. For example, I don't know, let's use the line objects, right, with an initial argument of 0. I'm going to have 2 of these, and these are going to create ramps. If you don't know how it exactly works, you can always right-click it and look at the help file. But I kind of know how it works, so I can simply say, okay, take the first one, start with 2, so 2 comma, and then go to 5 over 10 seconds, so 10,000 milliseconds. And the second one can start with 4, and it can go to 1.44 over, again, 10 seconds, so 10,000 milliseconds. And to make these trigger at the same time, I can use a button, and then suddenly we have these cool Chladni patterns that are evolving over time. You can have more fun with this, right? You can tie this to, for example, musical parameters and analysis of the incoming audio, maybe some kind of pitch detection to figure out what this ratio between the 2 parameters can be. You can also use the vibration parameter we have set. And normally that would be something like 0.1, but what if it's 0.5? It moves more, right? There is more vibration, so there is more background noise. Or what about 1.8? Or 1 or 10, and then it's very, very, very chaotic. And if I start over by clicking this jit noise, nothing happens. So you usually want your vibration to be something low. And the last thing we can do to make this really beautiful is to constrain the movement of the sands to a certain range. What do I mean by this? Notice that if I keep changing this pattern, it kind of expands, right? Because the sand particles are being pushed around more and more, so it's going to get bigger and bigger and bigger, reveal bigger patterns, which might be cool, again, if that is what you're into. But to keep this on a plate, at the final step of my jit.gen calculation, I'm going to use the clamp operator, or no, the clip operator, which is going to, well, clip or clamp the values to a certain range, so it doesn't really matter. But I'm going to use -1, +1 as my arguments. So what this does is, essentially, if the particles are moving beyond 1 or beyond -1 on all of the axes, it just stops there. It cannot go further, which makes it look more like it is constrained within a plate. We can even create a plate, right? I can use the jit.gl grid shape objects. I can give it the argument of my jit world context, Cymatics, and I can use the shape plane. There we go. Now we have a plane. Of course, it doesn't look too appetizing. First of all, let's make it completely black. So color 0001. And then let's make sure both objects are controlled by the same jit.gl handle. There we go. So now it really looks like we have a plate with a bunch of sand over it. And as we change these parameters for the frequencies, more elaborate, interesting patterns emerge. So of course the natural next step is to tie this to a musical patch, right? Maybe some synthesizer patch, or maybe it's a live audio analysis, or maybe you're just using MIDI controller information to determine the ratio between these two frequencies. The point is you want to have two values or some kind of ratio which you can then apply onto this formula, onto these two parameters, in order to create cool, interesting, awesome patterns. I hope this has been interesting to you. I hope you have a lot of fun with it, and thank you for watching.